Okay, welcome and good morning everybody for this second day of this very excellent conference here in Paris and New York. And today we have the morning session, first with Professor Marylou Gabrié from École Polytechnique, and later on we'll hear the mirroring talk from the New York side from Rupert Croft. And in order not to lose so much time right now, I will hand over the stage to Marylou, who's going to talk about generative models to assist sampling and provides a tentative tutorial on this. And I think this is going to be an exciting talk on a very relevant topic, in particular for Bayesian inferences in cosmology. Marylou, take it away.
Thank you very much. So thank you very much for giving me the opportunity to talk about these methods. So disclaimer, I'm not an astrophysicist, so this talk will really be about methods, and I will try to give you a hint at this, and I'm definitely not aware about all that these methods have already done for the field of Bayesian inference for astrophysics, but so my talk will be really to try to give you ideas of why it could be a good idea, why you should maybe try, but also what we expect are the challenges, and so where we also need more efforts in the research in this direction. And of course, so I'm going to talk about some things I've done over the past couple of years and with many collaborators. I will name them when this shows up, but also try to speak about what others have been thinking in order to improve these type of algorithms that are trying to leverage machine learning, but a certain type of machine learning, right? Generative models that are currently seeing a surge of development in the machine learning community. So to assist us in our scientific computing tasks, and here, namely in Bayesian inference, where we need to do sampling. So to start with, I'd like to remind everyone, although maybe most of you are familiar with it, of what's a generative model, and also specify which type of generative models I'm going to be interested in these talks, namely deep generative models that work with latent variables and transport maps. So a deep generative model that works in this fashion has a base distribution that here I'm denoting by rho b, and that I know how to sample easily, so think high-dimensional Gaussian, for example, that I'm then transforming the realization of with a map that here I'm going to call T indexed by theta, such that I produce realization X that have a sophisticated distribution. So here again, I need to apologize because theta are going to be the parameters of my neural networks and not the parameters I'm trying to make the Bayesian inference of. I hope you will forgive me. And this push-forward distribution, therefore, is modeled by this combination of the simple base distribution and the transformation T theta, whose parameter I'm hoping to learn in order to have a rho theta that looks like something I care about. So you're probably aware of that nowadays, with this type of technology, we are able to learn transformation T theta that are going to transform images that are completely random noise into images that looks like, for example, dogs, and seemingly mimic the distribution that is underlying images of dogs. And this is the case because each time I'm going to sample a new Gaussian random noise image, I'm going to get a new dog picture of this learned distribution. So I really have a way of efficiently representing and sampling from a very complex distribution. So, of course, this is only possible after training, but here we are also, before I'm talking about training, I wanted also to specify yet another restriction of the type of generative models we are going to care about, which are invertible maps, transport-based models. So those models, they just follow the paradigm I was showing to you, but the difference is that I'm imposing that T theta is a diffeomorphism. And if I do so, then I can write down explicitly what is the value of rho theta of x using the so-called change of variable formula. So it's just something that if I was asking you to compute the integral, you would just do it without thinking, just saying, okay, I have a multidimensional change of variables, so I need to introduce the Jacobian. And I mean, this is just what this formula is. And therefore, it relates what's the density of probability of the push-forward distribution that is defined by my entire model with the density of probability of the base distribution, the inverse of the map, and the Jacobian of this transformation. Okay, so I will need to have access to that, so this is why I'm going to be restricting myself to this. Famous families of generative models that belong to this family are normalizing flows, and so as a shortcut, I will talk about flows a lot in this talk. But there are also continuous time versions that we could see as being in this family, although the formulas will be a bit more intricate because then we would be really needing to think of integrating over a process in order to compute, for example, this push-forward distribution. But just bear in mind that philosophically they enter into the same category of generative models, and those are, for example, neural ODEs, continuous normalizing flows, score-based diffusion models. Okay, and so just a hint at how those models are trained in the machine learning community. Well, you have, of course, a lot of data. You have a big sample, a big data set of images of dogs, for example, and then you can imagine different losses that are going to give you signal in order to adjust the parameter theta of your transformation such that the row theta that you're creating is looking like the underlying distribution of your training data. So if I call my training data X size, then I can have a maximum likelihood objectives where I will have a loss that looks something like this. Or I can also imagine score-based objectives that therefore I'm more matching the score, so the gradient of the log of the density. I mean, this is just to, I'm not going to enter into the detail, but it's just to cite some of the methods. But all of them rely on the hypothesis that you have a lot of data, so a lot of samples X size from the distribution that you are trying to model with your deep generative model. So of course, it's not going to be the case for us today. But okay, why am I talking about those deep generative models? Well, my goal is to do high-dimensional inference. Here, I will always assume that I have a distribution that is known up to a normalization constant. So the likelihood is tractable, the prior is lactable. If I place myself in the Bayesian inference framework, where I have here, again, the parameters that I would like to infer that are going to be denoted by X, the data, for example, by D, but here I'm always going to just put the data to the side, so I will only think about a row of X. But, I mean, as I'm sure everyone in this audience is very familiar with this type of motivation, that you have data, you have a model for your data, and you want to sample from the posterior of the parameters X of your model, given your data, in order to have an idea about the uncertainties in your parameter estimation. And I also come from a community where we care about those high-dimensional probabilistic models because we are actually coming from statistical mechanics and we want to specify the statistics of a system given an energy function. But I will think of these two problems as being the same in this talk, where I have a row of X, which is a target distribution I want to make inference on, and I know it up to a normalization constant. So, I mean, just to state the obvious, we know that direct inference is intractable because computing those expectations exactly that requires integrals over the space of configuration is obviously much too big and scaling exponentially in the dimension of the problem. And therefore, we have to rely on Monte Carlo methods. Sampling itself is still challenging. I'm sure I'm telling you nothing that you're not aware of, for many different reasons. Could be dimensionality, could be geometry of the posterior, could be multimodality. So we'll see how this enters into the picture and see how can we use generative model to speed up sampling. So we kind of have an intuition maybe, but let me really walk you through simple samplers and see on these examples how it could help. So if you think of a very simple sampling task, but that's at least has this multimodality issue. So here I'm taking it as a toy example, a bimodal Gaussian mixture of Gaussian. So I have two blobs in 2D. I'm plotting the marginals on the two axes. And I'm thinking of a simple sampler to try to obtain samples from this distribution, say importance sampling. So I don't know if everyone in the audience is familiar with importance sampling, but I can state it in 2 sentences. What I'm going to do is have a tractable proposal, a distribution that I can get samples from. Say I take just a centered Gaussian. Okay, I don't know why the version of the animation is not working. So what you should be seeing is a big blob of points that corresponds to having a Gaussian. So let me. So I have my 2 blobs. I say, okay, I want a tractable proposals. I know that with high dimension, even if I'm in high dimension, Gaussians are something that are very simple to handle. So say, okay, what I'm going to do is that I'm going to choose as a proposal a just big unimodal Gaussian and draw a bunch of points in them. Then I will have some points with good overlap with my target distribution, that were those 2 original blobs, and some points that are a bit here in the vague where I actually don't care. Well, the way importance sampling works would be to say I'm going to reweight all of those points, and I'm going to compute a weight that is W of xi that will be equal to my target distribution, rho of xi, over the density of my proposal. So here it would be the density of the Gaussian. And once I have computed those weights, I will realize that those points are going to take a lot of importance, and all of this one would be kind of wasted computations because I'm just going to attribute to them a weight that is equal to 0. But, I mean, I can use this method to compute an estimation of this expectation by just reweighting the samples in the sum. Very well. The problem, again, is just that I'm wasting a lot of computations, and I'm developing something that has a high variance estimator, because few points have a lot of importance, and most of my points actually don't matter. And this is obviously becoming more and more a problem as the dimension is becoming higher and higher, and that I'm having a bigger problem of having a wide enough proposal to cover all the space that I care about. Well, instead, what I can do is say, okay, maybe importance sampling is too simple. I can resort to Markov chain Monte Carlo. So what Markov chain Monte Carlo does is to rely typically on a local proposal. So here I wrote the proposal kernel of the Metropolis Hastings that corresponds to doing Mala. So Langevin adjusted updates, where I just, to go to xt plus 1, start from xt and then have a gradient update in the direction of decreasing gradient and add some noise, and I have this random walk that is exploring my space. So if I just try to replay this video, will it let me? Maybe only if I do it like this. So if I initialize a walker in either of these modes, what I'm going to see is this type of behavior where I'm creating 2 chains that are covering well each of the modes I'm caring about. Why the output of this simulation will still be unsatisfactory? Because actually my MCMC has not converged. If I'm what I would need to have an MCMC that has converged is that all the chains have visited statistically the same space. I mean, all of the chains have visited exactly the same space. They have mixed, and therefore, if I had an MCMC that had mixed, I could realize that one of the 2 modes that I put in my toy example was twice as likely as the other one. But right now, the likelihood of each of the modes that I'm observing is purely inherited from my initialization. So if I had initialized 10 in 1 and 1 in 1, I would have a ratio 1/10 for each of the modes. But as soon as I haven't seen any transitions and that all those chains have not transitioned sufficiently between the 2 modes, I'm actually having no idea of what is the relative weights of these 2 regions. So we have, with these simple samplers, big challenges, which is high variance for important sampling, and which is lack of convergence and decorrelation for the Markov chain Monte Carlo. Say now that with the same problem, I'm giving you a model that ensures that rho theta is close to rho x. So here, rho theta is my deep generative model that I've trained successfully to be close to rho x. So for example, I obtain something like this, which is with a simple normalizing flow. And it's not perfect, right? It doesn't look like rho of x, but it has a high overlap with rho of x. So if I'm doing important sampling, so here again, it's not going to work. But what we would be seeing is that I'm not creating anymore all these points. And I'm basically creating points only where I have some gray level sets. And I will have some in between where I have this kind of artifact of my generative model. But most of my points will be actually in the regions I care about. And so the variance of the estimator I'm creating by computing the weighted sum of the W xi's, f of xi's for any f function I'm interested in computing the average about, is going to have much lower variance by the fact that I was able to adapt my proposal to have a very close overlap with my targets. Okay, so that would be actually quite nice. Now, how about the Monte Carlo, the Markov chain version of this, of using a deep generative model to help in my sampling? Well, what I can do now is to rely on a global proposal instead of the local proposal I was showing before. So here, what I would do is simply say that my propositional kernel that proposes me to go to xt plus 1 knowing xt is going to take the shape of a rho theta of xt plus 1 that is not even conditioned anymore on xt, but just trying to jump somewhere in the density of probabilities that is modeled by the deep generative model. So if I were able to train a model like this one, I can imagine a Markov chain where I just jump freely anywhere in this distribution that I can sample proposals from. So if I do this, now my metropolis Hastings start looking like this. I have mixing chains in between the different regions of interest, and therefore I'm going to be able to retrieve the statistics that I care about in this system. So here, I'm hoping that I'm convincing you that if you can train rho theta such that it's close to rho of x, what do you gain? A lot. Are there any questions up to here? No, so far so good. Okay, so what you should be asking yourself, but that is coming next, is, well, suppose you can train, but how can we train? And you say rho theta close to rho of x, what do you mean? What is this criteria, these vague criteria that you're giving to us? So here there is something that is very different from the paradigm of deep generative modeling as it has been developed in the machine learning community. What we have is a target rho of x, so that from now on I'm calling rho star of x to differentiate what's the target and what are the other distributions coming up. So I have my target rho star of x, which I know up to a normalization constant, but I precisely don't have samples from rho star of x because this is what I want to get from my algorithm. So I'm not in a regime where I have all the data I want in the world to train my generative model. So how can I train? And the second thing I think we should care about is the rho theta of x close to rho star. Well, in the deep generative modeling, that again has been driven by applications such as generating real-world images, generating text. I mean, it's very complicated to generate an image that would look, like a real-world image. But in a sense, it's not as stringent than to generate a molecule, for example, the applications I care about, that would actually be a physical molecule. So in a sense, we have criteria of success that are a bit different. And so here, we really need to care about it. And for Bayesian inference, we would really need to also make sure that the algorithm that we have is indeed, that we, as an acceptable variance, that you can show that the sampling procedure is actually made more efficient by this training. It requires a criteria like this that is a bit difficult to grasp at first. So let me try to tell you a bit about these two stories. So, I mean, there is actually a very natural idea that has been around for more than a century of how to fit parametric model, probabilistic parametric model, without data to a target distribution. And this is variational inference, mean field variational principle that I think is the first reference I know about it. I know about that was by a paper by Pierre Weiss in French in 1907 that is around this idea. But I mean, we can state it very simply, despite all the different contexts that I've used it. That is that I'm going to take a criteria that is the Kullback-Leibler divergence of difference between my two distributions. So the target rho star that I know up to normalization constant, and my model rho indexed by theta, so the parameters of the neural networks that enter into the definition. And this Kullback-Leibler divergence, if I try to write it, it's actually an expectation over rho theta of x, so my model. And so it means that if I want to approximate this loss function, the only thing I need to do is to sample from my model to have a Monte Carlo approximation of my loss function. This is something I can do. And so I can actually write a loss function for my parameters theta that are going to, ensuring that if I do gradient descent on these rho thetas and this Kullback-Leibler divergence between my model and the target is decreasing, and seemingly I can train, I don't need data. So if I just look again at my very simple toy example, and I look at what happens to the gradient descent if I initialize it this way, so as a just big blob for my rho theta, and I update the parameters of my normalizing flow that is underlying this simulation to follow this criteria, I would see something like this happening. So not bad, no? I mean, the model, without any samples from rho star, has managed to extract from the rho star terms that comes inside the training loss some information of where are the modes and produce mass in the model where I care about in the target. However, if I was to initialize my transformation, my simulation just this way, I just changed the initialization, I would see something like this. So actually, here again, I mean, and there will always be, no, we sense that there is an initialization issue. And I mean, seemingly, it feels like you could, so this is what we call mode collapse in the community, where we ended up by having learned a model that is only concentrated in parts of the underlying distribution that we care about. And seemingly, you could think, okay, but that's fine. Maybe I can just have an initialization that is always much wider than what I think I will care about, and things will go fine. But actually, it's more complicated than that, because first, it's not entirely understood where this mode collapse comes from. I mean, there's definitely questions of non-convexity that are underlying, but there is also interplays between the parametrization, because if you look at the objective, it's convex in distribution, but you're never actually modeling a distribution. You are modeling, I mean, putting parameters to a distribution, and this is where the non-convexity comes from. And what we see is that it's very hard when you are in high dimension to follow this objective, and even with a wide initialization, not end up with mode collapse. So, okay. So this first idea, again, was very natural. I think the first person who used normalizing flows, so deep generative model, to apply it, to have this variational inference that I call on steroids, because you have to compare it to, say, Gaussian ansatz, that are maybe, I mean, Gaussian, mixture of Gaussian ansatz. I mean, what we can do if we don't have this type of deep neural nets in the middle. So I think the first person who applied it is Danilo Rezende with his colleague from DeepMind in a paper that is called Variational Inference with Normalizing Flows, but it has been used by many other groups since then. So the second idea that I was involved in is to instead rely on adaptive Markov chain Monte Carlo methods. And it's an idea where you are going to simultaneously converge a training and converge the sampling of your Markov chain. So to do this, we went back to the maximum likelihood objective of training, which is seemingly, that is actually equivalent to thinking again of a Kullback-Lablo divergence, but where I invert the order of the terms. I used to write at the previous slide DKL rho theta rho star, and now I'm writing DKL rho star rho theta. And it's actually something that is written as an expectation over rho star, and that I can approximate by a simple Monte Carlo if I have samples from rho star. But here I am back to the chicken and egg problem. I don't have samples from rho star. I say yes, but little by little you will get some. So how do? You still start with this simple objective, and you start to run this local Monte Carlo that I was telling you was not enough earlier. I just write my local Monte Carlo, and I develop data sets that locally are consistent with the target, but somehow are missing some global information, say about the relative weights. Never mind, I still use them to train a first generative model. I obtain something like this. And then, in turn, I can use this generative model to power a powerful Markov chain that this time will use a global kernel and retrieve this global information that was missing. So now I can, so the movie won't play. It will play, okay. So now, so first step, local. Second step, train. Third step, global sampling. And in practice, what you do is just that you repeat those operations, not converging each one of them, but just doing little steps of each one of them interleaved and looping over them in such a way that you get such a global algorithm, global local algorithm, where you are alternating between different types of kernels and with training steps of your generative model, and you obtain a simulation that will be converging in this fashion. Okay, so I said it belongs to the adaptive MCMC literature, because the adaptive MCMC literature is exactly this, learning from the chains that you are creating how to update your kernel such that it's more efficient. So I think the first proposal of adaptive MCMC was to update the covariance of a Gaussian random walk for the proposals that you are just taking. So here it's, again, adaptive MCMC on steroids. You're not only updating the covariance of a local Gaussian random walk, you're learning a global kernel that is going to allow you to shoot everywhere in your space in order to have mixing algorithms between the different modes, between far away regions, and so on and so forth. And so I call it also a global local algorithm, because eventually here we are not only relying on the flow, right? We are also relying on this local kernel that is really a mediator to create data where the flow hasn't yet been in order to have something that is as complete as possible. So far, so good. You should be telling me, wait. And why? Because here, what I did in the previous simulation is that I initialized I initialized two walkers, one in each mode. If I were not to do that, and I was going to only initialize one walker in one mode, the outcome of my simulation will be the following one. So here, there is really no free lunch. There is no mode discovery mechanism in this method. It states that if you are able to identify the basin of attraction you care about and to start one chain in each of them, I don't say that you need to know the shape of the basin, you don't need to know its size, you just need to be able to have at least one chain that has fallen into it, then you will succeed. But otherwise, you won't. Okay? Okay. So a third idea that has also been investigated by several groups is to join forces with annealing or SMC. I should not put an acronym in the title, I apologize. SMC stating for sequential Monte Carlo. So the idea of the annealing procedure would be to say, if I look at my target as being something that looks like statistical mechanics with a temperature, I mean, you can always rewrite to posterior such that it looks something like this. Then what I can do is imagine a temperature that is higher and where I believe that I'm going to be able to smooth enough my landscape to converge a simple Markov chain. And once I have this, I can train a model at this first high temperature. And once I have trained a model at a high temperature, I can use it as a proxy to power a Markov chain at a slightly lower temperature. And so on and so forth. You're trying to decrease the temperature by training models seeded from a very high temperature where you know you can sample, and then using generative models to decrease the temperature little by little. So this is, for example, a work by the group of Pilati that has done this back in 2020 in the context of disordered systems from statistical mechanics. But in the context maybe more of Bayesian inference, there is the group of Arnaud Doucet that has also worked on a solution that they call annealed flow transport that has actually more a taste of sequential Monte Carlo, where here, I mean, I stole this picture from a slide by Michaela Arbel that is one of the, I mean, formerly students, but now INRIA researcher involved in those papers, where you have really the picture of this annealing procedure where the distribution you care about is maybe here with this blue color. But you start from something that looks like the yellow one, and gradually you are going to target a distribution with decreasing temperature that is going to look like your target, and where what you're going to do is to learn intermediate models, intermediate flows to help you in the sequential Monte Carlo procedure to transport the mass little by little to the target. So, I mean, I'm not going to try to give you more details about these methods because they are quite intricate. But the general comment is to say that they are probably extremely robust, in particular, probably quite robust to this mode collapse phenomenon, or even able to find modes to a certain extent. But they are also more costly and more of a machine to be engineered because you have to do things at several temperatures. In the second case, train several models. So things are a bit more intricate, but probably more robust to be tested. But I think, okay, and one work I also absolutely need to be citing is from the astronomer community and people caring about of inference methods, at least like where I stand from. There is worked on preconditioned SMCs, so preconditioned sequential Monte Carlo, that are along this line with yet another flavor, but I will come back to preconditioning. And this is from the group of Uro Serjak in Berkeley. So far, so good. Okay, so here I told you about this first problem, suppose you can train, and I gave you kind of 3 big ideas about how you can imagine training models without a priori having a large data set of samples from the raw star of X that you are trying to approximate with your deep learning model. Now I'll just take a couple of minutes to tell you about examples of how we can do this in practice, biased towards which I know, so it's really completely biased, but just for the sake of giving you some concrete examples. So the first one that is actually in Bayesian inference and in astrophysics is the work of Kees Wong. So I'm not directly involved in this work, but it used the method of the adaptive MCMC that I co-developed, and who is trying to infer the parameters of gravitational waves using this type of approach, and that seemingly is competitive for real-time inference of these processes, where time might be might be at stake if you hope, for example, to one day be able to do inference in real time to be able to point new observing devices towards the events before it's over. So that's one thing that at least Kees is really enthusiastic about. So he's from CCA, so you know where to find him. And then the second example, so just to, again, give you a bit the landscape, that this time I'm involved with, is the issue of sampling molecular systems. So it's a full community of people are working on molecular dynamics and way of simulating molecular configurations. And one direction is to try to really describe what's happening in molecular system at the quantum accuracy. So where you are not building a model of springs that is kind of showing what's happening in your system, but really you are looking at the density of electrons and trying to describe how you can do your model. So those are simulations that are extremely costly, but where you can try, so with those methods, to still have some sampling going on by being as efficient as possible in the usage of the computational budget you have in your hands. And so one example would be the following, where you have two metastable isomers that are made of 6 atoms of silver. And what you want is to be able to understand what's the thermodynamics between the two, so how do they relate to one another at a given temperature. Well, if you use molecular dynamics, then you are only going to be able to look at the vibrations locally of each one of those isomers. So you have this pyramidal isomer, triangular isomer, and you can see it vibrates, but it will not transition to this kind of pyramid of 5+1 transition. But with this type of methods, you can create really an algorithm that is going to make a Markov chain that is going to be jumping between the two isomers and to understand the whole free energy landscape of this problem. So here, what I'm showing you just in one word is a plot where I have two projection coordinates of my system that are separating well the two isomers. And if I compare with another free energy approximation method that give me the landscape projected in these two coordinates, I can see that I can create a Markov chain in orange with my algorithm that is going to be jumping between states. Okay, so yet another type of applications. Okay, so now that we've talked about whether you could train, and that I've told you some keys about it, and I've shown you some example of where it looks like it's useful. Now, is it true that it's always going to be possible to have this rho theta of x close to rho star of x? And what even do I mean by that? So what I've put under the rug so far is what happens when you really code the algorithm and you really look at it and you want to diagnose whether or not it's any useful to you, and if you should have spent the time designing your neural network architecture, choosing the hyperparameters, and so on and so forth. So if you stick to the first algorithm I talked about, which is what we could call neural importance sampling. So you do importance sampling where your proposal is a deep generative model. Then one key observable to look at is the participation ratio. So how is this participation ratio defined? Well, you have your so-called self-normalized importance weights that are those WI. And those WIs, as you can see, so they are the W x's I had noted here down, but that I also renormalized by over the full set of samples I had, if there were n of n, and n of them, I'm just summing the value of the unnormalized weight to it, such that it's self-normalized, because here I'm making the assumption that I don't know the normalization constant of rho star, so I need a normalization criteria. But okay, so if I have those weights for each one of my sample, then what I can do is compute this participation ratio that is going to be equal to the sum of the weights to the square over the sum of the weight square over n. And it's easy to see that if you have all of your weights that are equal to 1 over n, so this would be the case if you had rho star that is equal to rho theta up to a proportionality constant, then you would have your participation ratio that will be equal to 1, so that would be the ideal case. Every one of the samples that you are going to propose are going to contribute equally to the Monte Carlo average that you're going to do. And here you have the optimal algorithm with the lowest variance as possible, given the number of samples you can afford to sample. But if you are in the other extreme case that you have W1 that is equal to 1 and all the rest that are equal to 0, well, this participation ratio would actually be equal not to 0, but to 1 over n. And so looking at this participation ratio tells you a bit where you are situated in terms of the performance of your algorithm, and namely, whether you are close to this rho star is equal to rho theta objective. Okay, so it's a proxy to understanding the variance of your algorithm. So that's one thing. Now, if you were to actually prefer to do a Markov chain to exploit what your normalizing flow or generative model has learned, then what you would care about would be the acceptance rate of the global proposal, right? So I remind you that the Metropolis Hastings acceptance criteria has the following shape, that if I propose to go to xt plus 1, given that I was in xt, and that I propose this with a density rho theta, and that my target is rho star, then I need to compute the probability of acceptance. That is going to be a minimum between 1 and a ratio. So a ratio that balances out what is the probability in the target of where I'm trying to jump versus where I used to be, but also what is the probability that I generated this move. So what is the probability that I propose to go to xt plus 1, and what is the probability that I propose to go to xt. And if you accept with such probability, you can show that the Markov chain converges to sampling from rho star under a few more assumptions. But it's going to be the thing you care about, because say that on average your acceptance is 0. Well, you've spent a lot of time designing your neural network and training it, but your output is 0. You're not managing to power your Markov chain kernel with your global proposal. You're just never accepting, and this is because it's not good enough. And similarly to the participation ratio, if I had rho star that is equal to rho theta everywhere, then I would have my probability of acceptance that would be 1, right? So monitoring how far away is your acceptance from rho star is telling you how good is your model and how useful is your model to your objective, which is to have a fast decorrelating Markov chain that is actually mixing. So that's the two things you should care about. Now, what is going to make the method fail, precisely, as I was trying to hint it, it's those discrepancies between rho theta of x and rho star of x. And where is this going to happen? Well, if you have posterior target distribution that are too intricate to be represented, so I don't know, you have very sharp walls that you don't manage to engineer into your model parametrization. I mean, some things that you expect your model doesn't have the expressivity to represent. Or if you have a very high dimensional model, it's unlikely that you're going to, with this training procedure, have a model that is precise enough to actually be able to jump in high dimension, which is kind of a very greedy, a very ambitious project to say that I have a model that allows me to just shoot completely independently in a high dimensional space and retrieve configurations, values of parameters that are actually valid and useful for my Monte Carlo estimation. So a question becomes, can we be a bit less ambitious and still take advantage of the generative models? So here it's, if you want, yet another method, once you have trained your generative model, to make sampling on them. And I will be very brief because my time is running out. But the idea is to precondition local samplers with transport map flows. And it goes as follows. So you have a base distribution that is simple. And you have a target distribution. Here, say it looks like a banana. If I trained my transport map well, I expect that this base, through the map, will be sent to a push-forward distribution that I just remind you the definition of, but that is looking closely like my rho star. But then I can also think of the reverse map that is sending my target distribution by t theta minus 1 to a pullback distribution that, if I'm successful again, will look like my base distribution. And it turns out that what you can imagine doing is sampling in this so-called latent space with a local sampler, and then send back your samples to your target in order to have a converged MCMC. And this is a method that has been actually proposed several times. I think the term that I'm keeping is the one from the paper by Matt Hoffman that is called neutralizing bad geometries with flows, and that inherits from this Nutra MCMC. And again, the idea is to say, okay, I'm observing that now I have a learned map that allows me to transform a complicated distribution into something that looks like a high-dimensional Gaussian. Well, let me try to sample this high-dimensional Gaussian, or this close to being high-dimensional Gaussian, with a local sampler, because I know that they are very good at it, right? We know that local samplers are more robust in high dimension and greatly help by preconditioning, so where I just squeeze back all the mass into being something that is isotropically conditioned compared, unlike, for example, this banana. Okay, so I have 2 papers this year where I really tried to understand whether or not this was a good idea. So, I mean, I will not take so much time to look at them, but what's the conclusion? The conclusion is that, yes, it's more robust if you have one-dimensional, unimodal distribution to actually do things by preconditioning and then remaining local, instead of trying to jump very ambitiously independently in the entire state. But however, okay, so it's a shame because the images are not showing, but there are 2 images showing you that here, the learned transport map do not erase multimodality. Let me try. I think I have one backup slide where it is, yes. So, but here you can see that the learned transport map, if I'm trying to model a multimodal distribution, typically don't erase the multimodality. So this is my base, this is my target that is multimodal. This is my push forward that has a nice overlap with my target, but you see the artifacts. But more importantly, you can see that the pullback has still a multimodal behavior, I mean, and even a geometry that you don't expect a local sampler to be very, very accurate at sampling. So it's actually not a good idea if your model is, if your target is multimodal. But what you could also try, imagine doing, and so this last work was something we published at ICML with my student Louis Greniot, and the second work is the one that has been accepted at an URIX workshop with my second PhD student Christophe Schonler, where what we tried is, instead of doing something that is a local gradient-based MCMC sampler in the latent space, would be a metropolis within Gibbs. So it's partial updates of the latent coordinates that actually allows you to jump through the different modes. So again, I mean, it's just to try to pique your curiosity, but I don't expect that you're able to follow my rushing into my final time. There are 2 Python packages if you're curious to test those methods that I'm aware of. There may be more. If you know more, please send me an email. And that you can pip install. One is based on JAX. It's been developed by Case Wong, myself, and Davin Forman-Mackey. And it's called FlowMC, and it's on JAX. And the other one is from the group of EuroCellJack, and it's called PocoMC. So they are implementing slightly different methods. Both of them have documentation. So we are at a high level of trying to diffuse research into applications. And we are certainly very happy to get feedback, at least on FlowMC, where I'm involved in. And if I just conclude, I think what we can say is that progress in generative modeling suggests that there is a way to having machine learning in N sampler. Where we see the catch is that it might be difficult to reach the level of training algorithms accuracy to make those algorithms work if the problem is too complex, too high dimensional. I would say that if we look towards what's going on in the generative models community, there are definitely ways of adapting these methods to continuous time generative models, although what somehow I had on the, here in all the examples were discrete time normalizing flows, but they are costly, so we start to see those papers appearing, and I mean, I'm trying myself, but it's not entirely clear that it's a better idea to do it in continuous time. Of course, there is no free lunch in finding modes, so that's, again, something I really need to state. And finally, I think I should end in an optimistic conclusion, which is that for Bayesian inference problems that are in moderate dimensions, I think these methods are really well suited and can work, I mean, pretty easily. So I think it's really good news. And with this, I would like to thank you very much for your attention, as well as my collaborators on those projects.
Thank you, Marylou, for this brilliant presentation of generative models, the many pitfalls and solutions that are available. And now I give the audience the chance to ask questions. Thorsten.
Yeah, thank you. This is fantastic to combine the best of both worlds, machine learning and statistical mechanics. Suppose you answered my first question, to which dimension you can go. Suppose I have a reasonable variational inference approximation in a million or a billion dimension of a multimodal problem. So I have it for one mode and I have it for another mode. Can I use this idea in order to connect these two modes and get a relative weight? I think there's no chance to find a normalizing flow which covers both in this high dimension, but I have the modes, I can calculate local probabilities. So you're nodding, that's a good sign,
yes.
but how to do it?
Yes, so actually the way we are already doing it in this molecular application I mentioned to you, where training two models is not something that is, it's not the computational bottleneck of the problem, is that if you can afford to train as many models as you have modes, then what you can do is then combine them afterwards in using a mixture model. So what you do is you say, okay, my actual rho theta is, I don't know if I need to write it, but my rho theta of x is actually going to be promoted to something that also have weights, and I'm going to have a sum over my modes k of. So if I have this, I don't know how to do the last method I proposed to you, that is to precondition and look at how to do the transporting the measure and then doing things in the latent space, because here I cannot transport everything. It's not written as a transport problem. But if I want to do importance sampling or Markov chain with a global proposal kernel, you just can do everything I said, but you replace rho theta with this. And you can adjust the parameters along the way if you want to know the relative weights. I mean, they will come up from your samples, but you can also, to be more efficient, learn them during the process. But I would say that for me, the big question, and I'm very curious, I'm very happy to talk about it, is what you call a reasonable variational inference approximation. Will it be reasonable in the two key observable I've mentioned, which is this participation ratio and this independent metropolis hastings? Because if not, I'm not sure I know how to do.
We can talk about this.
Yes, I'll be very happy. Yes.
There was a question over there.
Yeah, hi, thanks for the really nice talk. So in your last, in this thing that you were talking about adapting, like sampling in the latent space and then transporting to, so basically the issue is that with the normalizing flow, you can't get discontinuities essentially between so you have this artifact.
Yes.
So is there something, so basically it's two questions, is there something you can do in the post-process, like kind of identifying this as an artifact and removing it in some way? And even if you have that, you had some multimodal thing in the latent space, but are you still gaining something in doing that, even if it's not perfect, basically? So
yes, it's a very good question. So I mean, the artifact where I'm thinking of sampling in the direct space, I don't, and I'm going to do something that is going to be global using this push forward. I don't really care because they don't have so much weight in my overall probability. So I'm going to sometimes propose in them, but I'm going to reject. But it's not going to be overwhelmingly all the time, so I don't really care. But the problem is really, if I were to think, okay, this is not working, too ambitious in the direct space, so I want to try to just do something in the latent space in precondition, well, there I really don't know how to transform this into something that Mala or HMC is going to be happy with. This being said, if I'm not thinking of 100 dimension, but I'm thinking of 10 dimension, with enough noise in your Mala or HMC, I think it will cross those barriers because things are still concentrated. But then, I mean, if you are in low enough dimension, why not do something completely independent and directly do it this way? So yes, you would gain, but and then it's probably also a question of the test of time, right? If those methods start to be widely adopted and tested in many different problems by people that don't know all the intricate details of this method, which one will happen to be more robust, which one will kind of win the race? I don't know, but I'm very excited to find out.
I think Matt had a question. Axel, are you informing me? Is there something on Slack? Okay.
I have a question. So one regime that we're really interested in field level inference is like a super high dimensional, like 1 million dimensional posterior, for which we would ideally like to generate a lot less samples, like 1,000 samples or something. Do you have any idea if any of these methods are useful for that regime where you actually want less samples than the total number of dimensions, even if you have to make an assumption that your posterior is unimodal or something?
So I don't think it's so easy to do it because the problem is not even, I mean, I'm not sure where is the problem is definitely that you're going to have trouble learning a posterior model that is close enough to your posterior that lives in millions of dimensions. And so the problem might be that you don't have enough samples, but it might be also in your parameterization of your model. So there are different levels of approximation that makes it that it's hard to make this. So I don't know that it works. I think the only work I know, but again, I'm not an expert, so maybe there are more, is one by Chirag Mogi from CCA also, and that has tried to apply this type of methods. And I think he combined it with different things. I don't remember exactly the details, but I would suggest to ask Chirag.
There was a question over there.
Hello, thank you for the great overview. Could you say a few words how nested sampling would fit into this bigger picture and how machine learning could accelerate these kinds of methods?
Yes, so this is where I'm going to shamefully have to admit that I've never gotten the time to understand nested sampling, so I cannot answer. But I know that this is something that I should because it seems to be precisely the go-to algorithm for many people in the astrophysics community. So if over the coffee break I can ask you to make me a first overview of what is nested sampling, I think it would be great.
Are there more questions? Axel? Then I have a final question. So for all these kinds of trainings, especially for high-dimensional training sets, so we are talking millions of dimensions here right now, we try to do this, and I actually observed there's this valley of pain, I call it. Initially, you start accepting, and then you start getting better, and then the rejection rate of your Metropolis Hastings sampler goes down. And it depending on the dimensionality, it actually goes close to zero, and it takes enormous time. But then if you basically can guarantee, let's say, 10% acceptance rate of that, then you have an exponential learning, and it happens. Is there something to this? Just a matter, is this just dimensionality, or is there more to it?
So I think you have things to teach me about it, so I will be happy to ask, but maybe just a comment about the fact that at first you accept and then it goes down. I don't know if this is something you have also analyzed in this fashion, but my intuition would be it's because the way you start your Metropolis, it hasn't yet found the typical set, and so it's just, yes, it's better. Actually, where am I? It's not that good, and then it has, so I think that's what's happening, but if you agree with this analysis, then yes, I'm happy to chat about what you've tried.
Perfect. Then I think we are at the end of the talk. Thanks, Marylou, again. And
Thank you very
please
much.
thanks the speaker.